Have Prahladh tell us about composition in PCP Constructions.
Good afternoon, everybody. Thank the organizers for giving me the opportunity to give this talk. I'll be speaking on the role of composition in low-error PCP constructions. Unlike the other talks in this will only be focused on PCPs and not to do. I won't have any cryptographic sort of constructions based on this. Just construction of PCPs, and primarily it's going to be the sort of how modular composition helped in constructing better and better PCPs. In the high error regime, this was sort of achieved by what are these objects called PCPs of proximity. In the lower error regime, this is achieved by something called decodable PCPs, and in fact, this will be the focus of the talk. Most of the talk will be trying to understand what these objects are. And one of the reasons I'm sort of giving these talks is not only have these objects, these sort of modular forms, these sort of PCPs of proximity, not only gave rise to PCPs with very low error and all, and gave a modular viewpoint of this one, they also led to the current best shortest PCP constructions known. So in both these cases, they give rise to the nearly linear sized PCPs, which is best we can. So in that sense, these objects might be helpful even in towards what constructing the rest of this workshop, coming with short PCPs, this one. So what we'll look at for the most part of the talk is trying to understand decodable PCPs. We might spend a little time on PCPs of proximities also. In fact, decodable PCP sort of generalizes the notion of PCPs of proximity. So just to quick reminder, what's a PCP? The PCP theorem gives an alternate characterization of NP. It says that any proof that can be checked by a deterministic verifier can be rewritten in a slightly longer fashion. This NP proof, which we'll call the probabilistically checkable proof, so that the new proof is now verifiable not by a deterministic verifier, but by a probabilistic verifier. So that's the sort of strengthening of the verifier, but you're sort of going to restrict the verifier by making it look at the proof at a very few locations. So it probes the proof at just a very few locations and is convinced of the veracity of the proof. In particular, if the input was a satisfiable instance, it's a member of the language, there is one such proof such that all the local views are accepting local views for this probabilistic verifier. And if the input is not in the language, then no matter which purported proof you feed to the probabilistic verifier, then most local views are always rejecting. The focus of our talk will be how small can we make, how large can we make this most. So is it like 0.1%, 1% of the views, or more like 99% of the views can be made reject? So in this sense, what is a PCP? A PCP is sort of a locally checkable encoding of the NP proof. In some sense, it is also an NP proof. It's a different NP proof, but it is something which is locally checkable. You can check whether the proof is correct or not by looking at it at very few locations. But where does composition play a role in all of this? So for that, we should understand how do we construct such PCPs. So typically, one of the most classical constructions of PCPs, today we know several other constructions also, arise from low-degree polynomials. These are one of most familiar constructions of it. So you use this following object, there is some function which I give on sort of a finite dimensional space, f to the m, a function, and the claim is this is a low degree function. How does one locally check this without probing the entire space? One very natural test is to just pick a random line and check if the restriction of the function to this line is a low degree function. Just using the main fact that the restriction of low degree polynomials to a line remains low degree. So I'm just formalizing the test. The test is, I'm going to give it with both the points oracle, which is this function f, and with an extra lines oracle. We are in the world of PCP, so we can give an additional proof. So we give up a lines oracle, which is the purported restriction, which is for every line I'm going to give sort of the restriction to that line. I'm going to give a low degree polynomial. And the test is the most natural test. You pick a random line and a random point on the line, query the lines oracle for the line, the points oracle for the point, and check that they are equal. And the low degree test, which is sort of the technical core of the proof of the PCP theorem says that if this, firstly, clearly this test has completeness 1. If the function is in fact low degree, then there is one lines oracle such that this passes with probability 1. But what we care for is the other direction. Suppose the test passes with, say, 90% probability. Can we say that the function is close to being low degree? And in fact, the low degree test analysis, soundness of the low degree test analysis says this is indeed the case. That is, if the low degree test passes, that is, if for a random point and a random line containing the point, the lines oracle and the points oracle agree, say with 90% probability, 90% of the time, then there is in fact an honest to God low degree polynomial that agrees with the function on most locations. Now, using this, we can construct a PCP, and in fact, this is what we saw in the boot camp. We saw starting from such a low degree test, we can construct a PCP with the following parameters: randomness log n, query complexity is either polylog n if you're going to restrict to poly size proofs, or n to the epsilon if you're working with nearly linear sized proofs. That's great. So already the low degree test gives us this, but however, we would want even better query complexity. In particular, if you're working with nearly linear sized this is not good enough for us. We would like to push it, drive it much lower. And here is where what we would like to do is we would like to reduce the number of queries. And composition is what comes in as a tool to reduce. So what do I mean by that? So let's actually look at let's look at this abstract notion of what I mean by reduce the number of queries. Let's look at the action of the PCP verifier more closely. What does the PCP verifier do? It gets as input the theorem that it wants to prove and some external random coins. Based on this, it computes some local window and a local predicate on the proof. It looks at the proof of that local window, and then accepts that that view in the local window satisfies the local predicate. Now, what we would like to do is we would like to check the first two parts don't involve reading the query. The second, I don't know why they're all 1, 1, 1. These two parts are the ones that are going to read the entire local view. We would like to test that the local view satisfies the local predicate without reading the entire local view. This seems very much like what a PCP does. A PCP checks if a proof is correct without reading all of the proof. So it was this idea of Arora and Safra from 92, which said just use another PCP to reduce this task. That is, if this were the outer PCP, use an inner PCP to sort of check to do this process. Don't read all the queries in this local window, but delegate the task to an inner PCP which is going to do this work. This is easier said than done. The inner verifier, notice that it not only needs to check that the local predicate is satisfiable, which is what a PCP is doing. A PCP is given a theorem and it checks if a theorem is satisfiable or not, as true or false. The local predicate, the inner verifier not only needs to check that the local predicate is satisfiable, but it also needs to check that it's satisfiable by what is written in this local window. So there's some sort of consistency issue that it has to this one, and this is done very delicately in this one. And typically what we'll show in this, we show that this consistency issue can be sort of resolved using what we will define called a decodable PCP. A decodable PCP will be sort of an extension of a PCP which will help us to do this consistency testing. Any questions so far? So what do I mean by a decodable PCP? Let's start off with a vanilla definition of decodable PCP. So the usual PCP is just this. It's a sort of an encoding of the NP witness. You take an NP witness and it's a locally checkable encoding of the NP witness. Decodable, so PCP is, so usual the PCP proof is just a locally checkable encoding of the NP witness. What I'm now going to add is not only should this proof be a locally checkable encoding of the NP witness, it should also be a locally decodable encoding of the NP witness. Because in the heart of this proof is somehow the NP proof. So I want to check if I can extract out the NP proof using this one. So formally, what do I mean by this? So the decoding PCP verifier, in addition to its usual inputs, which is the theorem statement and its randomness, is going to get a location, some index to a location in the NP proof. And it's now asked to either, if it rejects, based on a local view, if it rejects, it rejects. But when it accepts, it's not just supposed to say accept, but it's supposed to decode what the NP proof contained at that location. So this is what I want to mean by a decodable PCP. So at least this is what the semantics of the syntax of it should look like. It's exactly like a regular verifier, but it's also, in addition to this, given an index in the NP, the original NP proof, and it's asked to output, if it accepts, what is written in the corresponding NP location. Formally, what I mean is the following: that is, for every NP proof in the completeness case, there must be this I'll call it a decodable PCP, a dPCP, such that the verifier decodes correctly with probability 1 all the time. And soundness, what I'm going to say is, for every dPCP, both in the yes and in the no case, for every dPCP, there must be a valid NP proof such that the output, the verifier's output is consistent with Y. So notice that if the theorem was not satisfiable, there is no valid NP witness, so most of the time this should be rejecting. So what I claim here, the verifier should either be rejecting, or whenever it rejects, it should be outputting something consistent with the NP witness. For every dPC purported proof pi, there must be attached with it an NP proof. You must be able to extract from it an NP proof such that what the decoder does on this particular thing is always consistent with this one. It's inconsistent with it, probably with at most very small probability. Very small. Here, very small will be like 1 minus delta, but that's, yeah.
So maybe just to clarify the definition, would it be okay to just take a normal PCP and append to it a locally decodable encoding of the witness? Would that satisfy your definition? Just take any PCP and attach an encoding without doing any consistency checking between the two?
That would not, why would that would not satisfy the...
Satisfy completeness, so why wouldn't it satisfy some?
So I want to say that when...
You could just encode some totally other thing and this might still accept, right?
So I want to say that whenever it accepts, what I wanted to say, whenever it accepts, it should be accepting because of this particular NP witness. So previously if the theorem was false, this would be rejecting most of the time, which will be the case here too. But let's look at the S case, when the theorem is actually true. In that case, what I want to claim is every string, if any string causes the verifier to accept with probability more than 1 minus delta, that must be because most of the time I can actually extract out an NP witness out of that string. That's what I mean by this. So
in particular, you don't know whether the thing that was encoded is a valid witness or not after checking the PCP, I think. Yeah. And I wanted to ask, what is the quantification on J in the definition? Is it partly probability?
So the probability is going to be over R and J over here.
And the fact that it's average case J as opposed to worst case J is because it will be good enough for applications?
That's good enough for the applications. Worst case J makes it like locally decodable codes, which we don't. We're going to aim at rates which are better than what are achievable by locally decodable codes. This is important. So yeah, so I'm going to make it formal. Next one, so what we're going to have is, in the S case, this is what you have. It's always decodes to the valid NP proof. In the soundness case, for every decodable PCP, there must be an NP proof. There need not be an NP proof attached to it, such that the probability taken over the random coins of R and the index J, this should be J over here, probability that the local window rejects or outputs something, this should be bounded. So either it should be rejecting most of the time, or it should be outputting something consistent with this particular NP proof. So it should not be accepting and be inconsistent with the NP proof. That's all I'm claiming over here. So whenever it accepts, most of the time, it should be because of a particular NP witness. So you're tying down every decodable PCP to a particular NP witness. So if it accepts, it's because it has in its belly this particular NP witness. So that's not implicit in the original statement of the PCP theorem, but almost all constructions had this feature. So to get this out of the existing thing is very easy. So if you can massage all existing constructions to have this feature. And I want to say, once you have such a definition, so almost all, at least the PCPs constructed on the low degree test are almost automatically, they do have this extra feature. That is, whenever they accept, it's because hidden in them is the NP proof, and you can actually extract out the NP proof. You can formalize this. And now once we have this, we'll see how we can do composition.
Local, right? I mean, we have PCPs that when you, like for instance in Sudan, like when you accept, it is because there's a weakness somewhere, but maybe you can't get out like a corrected symbol with a small number of queries, right?
Benson-Sudan, yes, has it. It's not obvious how to make it a this one. You have to do something else. So it's easy when you're working over PCPs constructed from multivariate polynomials. For univariate polynomials and Benson-Sudan, it's not obvious, but you can massage them to construct decodable PCPs. Okay, given this object, how do I now do composition with it? Now there's a very fairly straightforward thing. So what is it? Let's go back to our problem. We had this proof pi, which we wanted to check. So the verifier, as before, computes the local window and the predicate that it wants to compute on it. But it's not now going to actually read all of it. Instead of checking the local window and satisfying, it's going to delegate this to an inner PCP. It's going to invoke a decoding verifier. So corresponding to each randomness of the outer one, there will be a corresponding inner proof. It's going to delegate it, and out there it's going to delegate it and pick a random symbol in this proof. And while checking that is correct, it's going to check that that random symbol is actually consistent over here. So this ensures the consistency across the two proofs. So it's this inner PCP's proof is trying to check that this predicate is satisfiable. Furthermore, not only is it not satisfiable, it's not only saying it's satisfiable, the witness due to which it's satisfiable, it's able to decode a bit in it, and then you just read a random location in this and check that that bit matches with what the inner PCP decodes.
You need some robustness from the PCP you started off with?
From the PCP you started off, you will need a robust PCP version. But for a yeah, you will need a robust. Yeah.
So why doesn't this blow up the size too much?
This is there only per randomness of this one. So it's like recursion. It's for you have a this is for each of the inner. So this is I'm going to add sort of say the original proof added an n square, converted an n proof to an n square long thing, and this itself was just polylog n. This is going to add a square of polylog n for every internal randomness, and that's fine.
I see.
Yes, for every choice of the random coin, I'm going to add a proof. The proof will be now this proof plus several of these proofs, but that's okay. It's just a concatenation of these proofs, and that's.
It's okay for polynomial time.
It's okay for polynomial time, and we will. Yeah, you'll see later on when you do it correctly. It actually there is no. It just grows by a factor of a linear factor. So that's going to be the entire composed verifier. The composed verifier is just going to invoke the outer verifier, but not read it in all its locations, just going to pick a random location. And as Ron said, we would need robustness. I'll come to this later. For now, let's just assume I'm sort of cheating over here. And I'm going to check the consistency across these two, and that's going to be the composed verifier. 1 second. So the query complexity of the new composed verifier goes from the outer query complexity, which is a fairly large number, to the inner query complexity plus an additional one consistency query.
You said that for each query on the first PCP, we build sort of
an inner BB. Yes.
Can there anything be gained from building one additional PCP that in sort of at the same time checks all of the queries?
So I don't know how to do this. It would be good if you could do it, but I don't know. So each one is checking a different predicate. So for each predicate, you have a different. So each one is checking if this window satisfies this predicate. And they all not only, even if they are the same predicate, they have to check that it is satisfied by this particular assignment. So each of them is being given a different task. So you're going to have.
You can't formulate the NP statement, which is the conjunction of all of the checks, and then build a PCP for that.
No, but that will not result. But then once again, you're blowing up the size. The whole point of here is this one. The input for the inner guy is just it's running on a formula of this size. If you're going to take a conjunction, it comes back to the old input, and there's no reduction in the size. Right now, suppose the whole point was suppose you had a PCP that had made square root n queries. You constructed an outer PCP which made square root n queries. You could recurse on it. This will have only 4th root of n queries because it has square root of n queries, so its input size is square root n, so it will make 4th root of n. If I take the conjunction of it, I don't gain any thing in doing it. So the whole point of this one is to reduce the query complexity. So you want to make the task of you want to make the query complexity smaller in this process.
The concatenation of all of these tiny proofs is a PCP for the conjunction of these queries. So I think, in principle, one could imagine doing it all at once, and you can only do better because this would be a valid solution to the
So
problem.
the concatenation is true, this one. Yeah, if you take the concatenation, but I must have a different way of checking them together in one
Yeah.
shot. Yeah. Actually, we will see some different ways of checking the concatenation later on. Yeah. Okay. And in fact, this outlined approach more or less gives us PCPs with constant query complexity, logarithmic randomness, and constant error. This is how this was done previously in the guise of using PCPs of proximity, but I just mentioned the whole thing using decodable PCPs, and you can do this. Question now which we'll ask is what about PCPs with very low error? I want to get error, I want to make the rejection probability smaller than half, possibly even sub-constant. This approach, we'll see why this. So firstly, we should have even decodable PCPs should be very low error PCPs. So how do we, so how do we get low error PCPs? There are two options to go about doing it. One is just take the constant error PCP that we have constructed, perform parallel repetition on a 2-query version of it, and you would get PCPs which have great trade-off between soundness and alphabet size, in fact, the optimal trade-off. But the main caveat being here that the proof size blows up when you use parallel repetition. It goes up enormously. So what we would like to do is a different approach in which we construct such a PCP directly from a low-degree polynomial, bypassing the need to use parallel repetition. And hopefully we get, the hope is out here, the proof size doesn't blow up as much as parallel repetition. And ideally, we would like to get the same trade-off. So far, we don't know how to achieve this trade-off between soundness and alphabet size when we construct such a low-error PCP directly from low-degree polynomials. And let's see how to do this. So firstly, to do this, I would need a low-error decodable PCP, in which this error now, previously the error was around 90%. That error has become like 0.1% now. So I need the exact same statement as before, but with such a low error over here. Now, if you look at it this way, what do I want here? For every string pi, I want to tie it down to one particular NP witness and say that its acceptance is pure. Whenever it accepts, it's because of that particular NP witness. Now, on the face of it, this is an impossible task to do, because I could take a proof which is in the first part corresponds to a PCP from one valid NP witness, and the second part corresponds to PCP from another valid witness, and it will accept with probability, say, about half or 1/3. So, but you will never be able to tie it to one particular NP witness. There are two NP witnesses which correspond to this. The question is, we cannot expect for such a soundness. The soundness requirement of such a dPCP has to be changed. We would need what is the list decoding version of the statement. We can't tie down a PCP, a pi to a NP witness. We could only tie it down to at most a constant number to a list of NP witnesses. And that's what we'll try to do. And the reason is the low degree test actually has this feature to it. So this was the low degree test which we said. And a refined analysis of the low degree test due to Rajan Safra and Arora Sudan showed actually that we have exactly the same problem. The probability that the test that is given any points oracle, there exists a short list of polynomials such that if the probability that the test accepts and it's not explained by one of these polynomials is very low. That is, whenever the test accepts, it is actually the reason for its acceptance is one of these polynomials. So this is the refined analysis of the low degree test was given by them, and once we have this, we can sort of change the soundness of the corresponding decodable PCP. We'll say for every dPCP pi, given pi, there's a short list of NP proofs, y1, y2, yl, such that the probability that it rejects and is not one of these guys is very low. In other words, the probability that it accepts and it's not explained by some element in this list is a very low probability. So such a PCP can, so once you construct a PCP out of the low degree test, it's very natural that you will get such a decodable PCP. And now we can go back to this one. You can ask what happens to yeah.
What's the optimal trade-offs between list size and delta here?
It will be 1 over delta, or order 1 over delta.
Is it easy to see why that's the case for very, very small delta?
This just comes from the fact that you use the Schwarzschild. It depends on, you're using the fact that it's not true for any particular list. It uses the fact that low degree polynomials have distance d over q. this one, and we are working with, this is not true for all delta, it's only true for delta which is polynomially larger than d over q. So I'm sort of fudging. So there will be but d over q will be set such that that will be vanishingly small, and then it will be just 2 over delta will be the leading term. Yeah. So it will depend. In general, you can always show this. This is just a, so this is sort of like it comes from the Johnson bound, or so. If you have a code, how many guys can? When it comes, it's a
simpler version would be to say that if you assume that there is totally no overlap between the different y's, different proof never agree, then 1 over delta is the right, because sort of everyone, each of them can cover a delta fraction of the proof.
Yeah.
You can just take you can take L different proofs and give each one delta fraction of the entries.
Yeah, so you get instead of 1 over delta, you would get 2 over delta, which is. Okay. So let's go back to composition, the same composition which we had before. So it was this, it's just that we have a strengthened outer and strengthened inner, both of which are working with very low error response. And let's just check if the same composition goes through. What I want to claim is actually it verbatim this composition goes through. You can do this. The only thing to observe is the error of the composed PCP will be the error of the inner PCP, inner decodable PCP plus L times the error of the outer PCP, because the inner PCP says if it doesn't satisfy, there will be L possible outcomes, and for each of them you're asking the error of the outer one. So this is the sort of error one will expect out of this. So once we have this sort of list size, this is the error which you would get. So the error of the composed PCP will be L times the list size times the error of the outer PCP plus delta. So as long as delta and the capital delta and small delta are small, this one is small. So you keep maintaining, you do composition such that this composition repeatedly such that this is quantity is small, and you will get a low error PCP. Yeah. So, sure.
Repeat the soundness argument, or at least the intuition for it. So why is this true?
So sound intuitive. It takes a while to prove this. So intuitively, it says, but for probability delta, everything that the inner PCP returns behaves like one of capital L outer NP witnesses. That's what the soundness of the inner guy says. And now you have to just say that these L guys correspond to L different proofs. Each of them have an error of capital delta, and therefore the total error is either the inner error or.
What's confusing me is that locally, once you fix the queries, this makes
you have to sew them together, and that you have to stitch them. The randomized stitching sort of works. That is, it works, and you get exactly this. Yeah. So it's just the fact that this is the inner thing. If the inner thing was perfect, you have it behaves as if they were L outer proofs, and it's one of and it's basically the error of one of them. So you have but you have to do this randomized stitching. That is, you come up with a randomized outer proof, which is one of these guys, and so it's a.
If you're aiming for like a really, really small error, then this won't work like right away, right? Because
no. So at this point of time, both this is small, and we'll be setting.
like 1 over delta inner.
L is 1 over delta, so you'll have to choose capital delta to be like delta square, delta inner square, and then use this, so that the total error will only be 2 delta inner. So you will choose the outer one with error. So the outer one has to be square of this. We'll come to this. We'll try to see how to get rid of this L also later on in the. We have to. How am I doing? Yeah. So if you do a careful analysis, we'll see that this actually gives you logarithmic randomness and low error PCPs. However, notice one caveat of this is each composition adds an extra query. Therefore, the number of queries the PCP will make will be at least the number of rounds of composition. The whole. So one will never get such of a 2-query PCP out of such an object. So what is observed is actually, so you can't get a 2-query PCP by this. So what we will show is if the composed PCP had this other property which we call robustness, which Ron had alluded to, I'll define it now. If it had this robustness property, then it is automatic, it is syntactically a two-query PCP. I will not go into what's definition. If you can show that the PCP that we construct has this extra feature called robust, it is actually a two-query PCP. Even though it might be making several queries, it looks in a different guise, it is a two-query PCP. And what is this robust PCPs? Let's actually go to this one. I'm just going to change the soundness. So what's the soundness which we had so far for a regular PCP? We said if the string is not in the language, then most local views are rejecting. But we'll just change it to state that most local views are not just rejecting, they are actually far from accepting. Most local views are far. In other words, the expected agreement of the local view with a satisfying assignment to the local predicate is very small. This is what. So this is what we'll call robust soundness. It's just going to strengthen the soundness of the PCP and says that not just that the most local views are rejecting, they're actually far from accepting. Formally, I'll just say the expected agreement of the local view with a satisfying assignment of the local predicate is very small. In the yes case, this agreement is 1. In the no case, I want the agreement to be as small as that. So this is what we'll call robust PCPs. Question is, do robust PCPs satisfying stronger criterion? In fact, almost all the PCPs that construct from polynomials do have this feature. The question which we would like to do is, does composition preserve? Because of this property, both the outer and the inner, if you are constructed out of polynomials, they will be robust. The question we would like to ask is, does the composition preserve robustness? If you have an outer which is robust and an inner which is robust, does the composed one also have robustness? So let's actually go back to our composition and check if it's robust. So is this a robust PCP?
Just doing a single query to that.
Yeah, single query. So you'll have to, you have to be a little careful. You have to distribute the queries. That is called, these are in two different alphabets. So assume they are the same alphabet, then is it robust? I want to say this can never be robust because the composed view always consists of two logical parts, one part into the outer and one part into the inner. And each part individually you can change it to make it satisfying views. Therefore, the robustness can never be smaller than half, say either any one of them. So as long as you have this sort of logical break, if the proof is broke, if the proof of the composed verifier, which is the outer proof plus the concatenation of all the inner proofs, it has sort of such a logical breakdown, then it's never going to be robust. So what we will do is, we're going to want to fix this around. So we'll go to one of these ideas of trying to check the different inner provers simultaneously. Why did we have the outer prover at all in this? Because we wanted to check that the inner provers are consistent with each other. Instead of checking it against the outer prover, we'll check them against each other rather than checking them with the outer prover. More formally, I just want to say this. Since instead of decoding from the inner prover and comparing it to the outer proof symbol, compare the inner proofs to each other. So you break this sort of logical split in the composed provers viewpoint. So what we'll do is, suppose this were the outer proof. This only now is in the mind of the verifier. There's nothing written down. It picks a random location in this proof, looks at various windows that proof location participates in, looks at all the corresponding inner PCPs, runs them and asks them to decode that symbol, and then just checks if they are all equal. So the outer PCP is completely disappeared. It's there only in the mind of the verifier. It picks a random location in it, picks various views that it participates in, looks at all the corresponding inner dPCPs, and then asks them to decode the same value and checks if the values decoded are. Okay? And that's going to be one. And it's not hard to show that this actually preserves robustness. This doesn't have a query complexity reduction as good as the previous one. The query complexity goes from the outers to d times the inner, where d is then sort of the degree of this, the number of number of local views that this location participates in. But as long as this is a reduction, we are achieving a query reduction. But on the other hand, this has the extra feature that it is robust.
So here it's important that we take all views that contain it, because if you were to take, say, half of them or less.
If a sampler will suffice, you just pick a good sample, and in fact, if you do all views, this will not be a reduction because If you look at it, if you construct the PCP out of low degree, this is like a point, and I'm going to pick up all lines or planes that contain the point. That's way too many. So that D will be too large if I do this on the PCP constructed out of the low degree test.
Before I wrap it up into the definition of a dPCP, I where is it like when you construct it?
No, at this point of time, instead of going over all this ones, you could just use a sampler to generate a generic sampler at this place. So instead of this, at this very step, instead of saying all windows, use some more extra randomness to pick, use a sampler to pick a certain number of windows and do it. That would have sufficed. But the error, so what would happen is you will get a sampler error over here. So just this will give you this error, the same error as what we had before. If you did it with a sampler, you will have a sampling, and the sampling error will enter. It will be this plus delta plus an eta, which is the eta coming out of the sampling error. Okay. Any questions? And once again, this the guy's question is sort of valid here. What's the intuition? Why is this true? It's the same. You'll do the same thing, that is. But for probability delta, all the inners sort of behave as if they are L outer guys, and then you come up with a fictitious outer, which is a randomized decoding of these L outer guys, and that you'll show that it satisfies with probability. It needs a delicate analysis, but that's you get exactly this answer. Okay. And so if you actually perform this repeatedly, you'll obtain the sort of the subconstant error PCP of Moshkowitz and Raz, who show that for every alphabet sigma and error delta, which is 1 over logarithmic in the alphabet size, there exists a nearly linear 2-query PCP over the alphabet. So what we have shown so far is that actually this gives you a robust PCP with certain properties. I didn't tell you what's the translation between a robust PCP and a 2-query PCP, but for this talk, let's skip that. A robust PCP by its definition almost is a 2-query PCP. Just a robust converted to 2-query PCP in which one query asks the entire view and the other query asks a random location in it. It's the usual transformation from a Q-prover MIP to a 2-prover MIP. But if this Q-prover MIP was robust, then actually this translation does not have any loss in soundness. The usual loss in soundness, if you go from a Q-prover, if you go from a 3-prover MIP to a 2-prover MIP, the soundness will deteriorate. If it was the original gap of 1 minus delta, it will become 1 minus delta over 3. There will be a reduction. But if the soundness was robust, then there won't be any reduction. And that's why we wanted the whole thing to be robust in this. And because of that, we'll get a 2-query. And this nearly linear just comes out as and added this one. That is, this is so modular in this one, there's hardly any extra randomness added. So if the original outer and the inner were nearly linear, there is no extra addition, more or less. You will get a nearly linear sized PCP in the whole process.
So how nearly is that?
So this, it's in the result of Moshkowitz-Raz, it's n times 2 power log n to the epsilon. So there's a multiplicative factor of exponential in log n to the epsilon. It's not n poly log n. It's better than any n to the 1 plus epsilon, but not n poly log n. Okay. So this is great. We can, using just these decodable PCPs and this idea of composition, we can get such good response. But notice the parallel repeated PCPs have a much better trade-off. They actually had a trade-off in which the error was inverse polynomial in the alphabet size, not inverse this one. And this is in fact what's the long-standing open problem, the sliding scale conjecture, which says that you can more or less achieve the same thing with a better error performance. The error is inverse polynomial in the alphabet size rather than inverse logarithmic. This is what a parallel repeated PCP will achieve, except it won't have nearly linear size. The size keeps blowing up. Here we do get nearly linear size, but with a weaker dependence on alphabet this one. So question you can now ask, can we get sort of a better trade-off between these two, yet maintaining the PCPs to be short? Okay. We can ask further this, can we further reduce the error that we obtained in this form? So let's actually try to, I won't be able to fully answer this. We won't be able to get it. This is still open. We don't know how to get a constant query PCP that has this feature. What we'll show is we'll get more or less such a this one if we allow the queries to be slightly super constant. In fact, we allow it to be log n, we'll get this. We'll be able to get this trade-off. Okay. And so let's go into where did the error of the robust composition arrive from. So the composition had this sort of error. It had, the error was L times the outer error plus the inner error. This was the error of this one. And this L, the factor of L appeared due to the list size of the inner dPCP. And if you're doing a constant number of compositions, this is okay. And as Amit pointed out, if you do super constant, this is going to blow up. In fact, it's going to be, if you do T levels of composition, you'll eventually have an L to the power T. And this can become, this is one of the reasons why these PCPs over here don't have as good a trade-off. One, you can ask, can we get rid of this L over here? Can we come up with a composition which will sort of get rid of this? Particularly, can we get list size 1? We saw that we can't get list size 1. We cannot pin down a decodable PCP to a single proof. A decodable PCP will always, with such small error, it will always talk about, it will have L different things. But can we still, let's see if we can, what I want to do is avoid the sort of something that looks like the union bound that arises because of a factor of L over there. So where did this L come from? The L came from the fact that any points oracle would have capital, a small list of low degree polynomials which would explain the full success of the test. So this is where the L came from. So that's basically, we had that equality. Whenever the low degree test passes, it is explained by one of the L polynomials except with probability delta. And that, because it can be explained by one of the L's, there's sort of a union bound that goes on here, and you get this factor L. But notice the fact that it can never be the case that it is explained by several L. For each randomness, each line could be explained by one of the L, but each line could be more or less explained by just one L. If it agrees with one polynomial, it's very unlikely to agree with. So the union bound is extremely wasteful over here. That is, for each L, I don't know which of the L polynomials it is. If I should have not used same letter L, same this one. For each line L, I don't know which of the capital L polynomials that it agrees with, but it at best can agree only with very few of them, typically only one of them. We want to sort of capitalize on this. We want to sort of say that because of this, we can further refine the decodable PCP and say that we're not going to lose a factor of L, but one. So what will we do? So, and this is because of Schwarzschild. This is explained by typically at most one polynomial. So what we'll say is we'll now show that because of this observation, we'll show that we can construct a decodable PCP with with a sort of a slightly different soundness definition, which we'll call distributional soundness. The previous soundness was the following, that is every PCP pi, dPCP pi, you can tie it down to a short list of NP proofs such that which fully explain the acceptance probability. Either the probability that it is not explained by one of these NP, the decoded value is not one of the NP witnesses, or reject, is very small. Now I want to say I don't have a list over here, but actually just exactly one from this. I can't do this. So what we'll do is we'll do the following. That is, I won't know which element of the list it is, but in general, but if I know which line I'm talking about over here, I know which element in the list I'm going to be. So basically we'll say that there exists a short list of NP proofs, but there's a mapping from the randomness of the decodable PCP to the list such that the probability that the local view is it passes but it does not agree with that particular view is very small. So it's not one of the elements of the list, but it's exactly this particular thing which is explained. So this is not it depends on the PCP and their choice of randomness. Each different random coin could have a different element NP proof that explains it. But once you're picking up the randomness, you're saying this is the NP proof that explains the local view. And so this will sort of help you to get over the multiplicative factor of L in the analysis. So you just redo the same composition theorem which we did before, but now do a super constant number of compositions. You will get sort of a refinement of an earlier result due to Dinur, Fisher, Kindler, Raz, and Safra. Basically, we'll get a polynomial that makes very few queries, super constant but very few, poly log log n queries, in which the error is 1 over polynomial, but the alphabet size is, so they have nearly a polynomial dependence. In fact, it's better than a polynomial dependence. The soundness is better than 1 over poly in the alphabet size. That's because we are making super constant number of.
Can you say a word about why this soundness property improves your composition, improves the loss in the composition?
No, so it's just the fact that in this composition, I will no longer have this capital L now. It will be delta plus delta.
Right, so why does this property mean?
No, so now I'm going, so when you're doing a constant number of compositions or a few compositions, as was done either in the old result or in the MR result, this will not really affect the error. But when you're doing a super constant number, the error is like, previously it was like L to the power T, and that shows.
The question is, can you give some, I mean, the sort of, at a high level it seems intuitive, but can you say a word about why the new property, the distributional, what is it, distributional
Soundness, yes.
lets you get rid of the L? I mean, you didn't explain the soundness analysis for the previous one, but why does the fact that kind of local views
so it sort of is, tell you in the sort of soundness analysis, when you're sort of doing this randomized thing, for each particular thing you will check which random view you're looking at, and you'll be able to decode according to that particular this one. It's a
so does it make it an
no, it's not an easier argument. It's not the composition in this. So this is the composition which Guy, myself, and Reet had. It's the composition. Once you set up everything, this one it still takes about 3 pages or so to show. This is syntactic, but it takes about. It's non-trivial to show it. You basically get rid of the L in that. This one, if you have the inner PCP has the stronger soundness, it's not easy to. Yeah, I should. It's not easy for me. I won't be able to abstract it out. This one, it just point of it shaves off the L factor here, and you will not notice this L factor if you're just doing a constant number of compositions. Both these will do. You will have to do a super constant. Therefore, you will have to do this one. Therefore, we'll have this. We won't get it. It would have been great if we won't be able to get it at the level of constant queries. We only notice this difference when we have poly log log n queries. And at that point, you begin having this sort of. What I wanted to say is this sort of abstraction out of decodable PCPs. So the fact that decodable, previously we had this notion of PCP of proximity, which led to nice composition of PCPs. Sort of replacing them with decodable PCPs, and the distribution soundness lets you give cleaner proofs. Not just cleaner proofs, sometimes it actually improves on parameters heavily. And it has the advantage that not only gives you the lowest error PCPs that we currently know, but also gives you the shortest PCPs. That just came for free in this process. That is, these things did not add any extra randomness, and so we got the shortest PCP constructions. Yeah, that's all I have to.
Do you have an intuition to share on why PCPs of proximity, why these do better than PCPs of proximity? Does it have to do with the fact that you have like statistical coding?
So PCP of proximity is sort of, it's tying you down to one proof.
This terminology lets you kind of work with lists.
It lets you work with more. The PCP of proximity ties you down with one proof. And in fact, the way PCPs of proximity were constructed was you construct a decodable PCP and just check, probe a random location and check that this one. So that already had tied you to one, and this one lets you, it's just the fact that this allows for less decoding of the proofs, that one did not. Yeah.
Do you have any intuition on what types of barriers separate us from sliding scale? Is it a question of more refined composition or better ingredients to plug into?
So right now I think this is my biased view, but I think the ingredients have to be improved. We have more or less got put them together in the best way possible, and I don't know how to put them together. So we would need something that improves on the ingredients. So basically we had this Reed-Muller based PCP, the Hadamard based PCP, and then the one coming from Dinu's gap amplification. These are the 3 building blocks, and we've been doing them. And I think we more or less, I don't know, we would need to improve on one of these.
So this whole trick with the distributional soundness allowed us to get the most out of the primitives that we know.
Yeah.
But to get the full sliding scale, you really need new primitives, new codes that are much more efficient, new tests.
Yeah, we need something better than code which has better rates than Reed-Muller and but still has the local testability features of Reed-Muller.
Can you phrase like a clean coding question that implies the sliding scale conjecture given the composition techniques we know?
I don't know how to phrase it that way because one question, of course, is you want locally testable codes there's a question of locally testable codes with constant rate, linear distance, and constant query testable. That's one thing. It's unclear because if I say Reed-Muller codes come with the advantage that they have polynomials. You could encode computations in polynomials. So I don't know how to abstract this out for an arbitrary code. So if it had this extra feature, then possible, but I don't know how to abstract this. Polynomials have this magical property which we've been using all throughout. Yeah.
Any more questions? Let's thank Prahladh again. Let's take a 10-minute break and come back for guys.